Every major construction project, from a skyscraper to a nuclear plant, is defined by a single terrifying question. How close are we to the tipping point? The lift plan might say the load weighs 50 tons, but the crane's actual safe capacity drops by the second as the boom moves, the wind shifts, or the ground settles. Failure is instant, catastrophic, and often fatal. A complex machine worth $20 million can be crippled in a single second. So when an operator is hundreds of feet in the air, how do they know the precise, dynamic, unseen weight limit of their machine? It's not guesswork. It's a non-negotiable legal document and a system of sensors so advanced it can predict disaster before the hydraulics can react. We'll explore these technical safeguards first, and then reveal the devastating truth of how a failure to account for wind caused a 408 metric ton section of roof to be dropped, killing 3 ironworkers. The foundation of every safe lift is the load chart. It's a non-negotiable legal/technical document in the cab, and operators treat it like a Bible. These charts condense hundreds of variables into a single capacity figure. For a 250 metric ton mobile crane, for instance, the chart may span multiple pages, detailing safe working loads for every conceivable configuration. Imagine a 50-meter main boom extended at a 60-degree angle with a working radius of 10 meters. The chart provides a specific metric ton figure for the safe limit. Extend the boom by just 3 meters, and the safe capacity might drop by nearly 20%. The core capacity is defined by the load moment, the force of the load multiplied by the distance from the tipping axis. The load chart is essentially a pre-calculated safety factor against that load moment for every possible machine geometry. The key takeaway is that capacity is not constant. It's a variable of the radius. The further the load is from the crane's center of rotation, the lower the capacity. An operator can safely lift a 70 metric ton counterweight at a 6-meter radius, but the crane might only handle 40 metric tons at a 30-meter radius. The physics of the load moment, the tendency to tip, is not exponential. It's linear with radius, but compounded by geometry. However, a piece of paper, no matter how detailed, is static. It tells the operator what should be safe. It cannot account for tiny, unpredictable changes during the actual lift. A real-world load may weigh 225 kilograms more than stated, or the outriggers may shift minutely. This is where technology bridges the gap between theory and reality, bringing us to the digital co-pilot of modern crane safety. The operator's initial task is verification. Before moving a component, they check the load chart against the lift plan's key variables, confirming the correct counterweight, verifying the boom assembly length, and ensuring the planned lifting radius falls safely within the chart's bounds. This procedural discipline, the constant scrutiny of the static data, is the first and most fundamental layer of the invisible safety framework. Knowing that a load chart is fixed and static, does the industry rely too much on these pre-calculated assumptions? And what happens when a new element, unknown at the time of planning, enters the equation? The single most critical technological device on any modern crane is the load moment indicator, or LMI, often called a rated capacity limiter or RCL. This system is the nerve center of the crane safety framework, providing the real-time dynamic calculation of the maximum permissible load. It addresses the fundamental question: if the load chart is the map, the LMI is the satellite navigation. The LMI doesn't just read the load, it continuously monitors 4 fundamental factors. First, the actual load weight, which is measured by load cells, specialized sensors on the hook block or fixed to the ropes, providing a digital readout of the actual force being applied, often down to the nearest pound. This is crucial because it accounts for rigging, slings, and any deviation from the estimated manifest weight. Second, the boom angle, determined by a boom angle indicator, a high-precision electronic sensor that feeds the crane's angle back to the computer. Third, the boom length, measured by a sensor system within the telescoping sections. Fourth, the radius, which the system calculates as the critical distance from the center of the turntable to the center of the hook. The LMI's onboard computer constantly compares the current load moment, calculated from the actual load and the actual radius, against the maximum permissible load moment derived from the programmed load chart. The result is displayed as a percentage of available capacity, typically on a robust color screen in the cab. Imagine lifting a 50 metric ton HVAC unit. As the operator extends the boom out an extra few feet, they see the capacity percentage climb from 60% to 75%. If the capacity approaches 95%, the LMI issues a visual and auditory warning. If the operator crosses 100%, the overload protection device automatically engages, initiating a controlled shutdown of the hydraulic functions that would increase the load moment, like hoisting or extending the boom. This hard stop prevents catastrophic failure. This real-time digital feedback loop is essential, but it doesn't work in isolation. The LMI is the brain, but the crane has other more fundamental protection mechanisms. For example, the anti-two-block ATB device is a simple but vital mechanical switch attached near the boom tip. Its purpose is to prevent the hook block from colliding with the boom head. If the hook block is pulled too close, it trips the ATB switch, which immediately cuts power to the hoist-up and telescope-out functions. It's a purely physical failsafe against an operator or ground crew member forgetting a basic operational limit. It's a testament to the industry's philosophy. Multiple layers of protection are always better than one single point of failure. But even with the LMI and ATB systems running perfectly, a crane can still be operating within its load limit and yet be fundamentally unsafe. The risk may not be structural, it may come from a hostile environment. The introduction of variable frequency drives, or VFDs, on some newer cranes has added another layer of precision, ensuring that the hoisting and slewing motions are smooth, controlled, and free of the dynamic shocks that can temporarily spike the load moment and compromise structural integrity. While the LMI governs load moment, other equally critical devices manage the environment and the machine's physical boundaries. On many construction sites today, the ability to lift the load is only half the equation. The other half is ensuring the lift path is clear. Enter specialized, yet increasingly common safety features. We rely on three primary situational awareness systems. First, anti-collision systems, often required in tight urban settings where multiple tower cranes operate over the same footprint. These systems use radio-based proximity sensors, typically UWB or RFID, to create a protective bubble. If a boom swings too close to another crane or a fixed obstacle, the system issues a warning and can automatically slow or halt movement. Second, zone/area limiting. The site safety manager pre-programs no-go zones, perhaps FAA-restricted airspace near airports or electrical transmission lines. If the operator attempts to swing the boom into this digitally defined no-fly zone, the crane is electronically restricted, ensuring the lift respects external physical constraints. Third, outrigger interlocks. On mobile cranes, stability relies on massive hydraulic outriggers. The interlock ensures the crane's full lifting capacity cannot be engaged unless all outriggers are fully extended and in firm contact with the ground. Without this lock, the crane defaults to a reduced capacity, protecting the operator from an accidental tip-over. Furthermore, the weather remains an unpredictable variable. Wind speed, in particular, is a crucial environmental factor. The anemometer, a wind speed monitor mounted high on the boom, is standard equipment and often required by manufacturer or site rules on many large cranes. Wind can turn a 40-ton steel beam into a sail, dramatically increasing the load moment and causing dangerous swing. When the anemometer detects wind speeds exceeding the threshold, typically 20 to 25 miles per hour, depending on the crane and load, it triggers an alarm, advising the operator to cease operations immediately. This small sensor provides critical data no pre-calculated chart could ever capture. In the end, the weight limit isn't discovered by one single device, but by a chain of systems. The load chart provides the static, theoretical limit. The LMI provides the dynamic, real-time comparison to that limit. And the suite of environmental and positional sensors ensure the lift remains safely within the prescribed working envelope. The complexity of these systems is matched only by the price tag. A full, state-of-the-art LMI system upgrade for an older crane can easily run from $75,000 to $150,000 or more. A brand new, heavy lift mobile crane, say a Liebherr LTM 1750-9.1 with a 750 metric ton capacity, can cost around $6 to $7 million. This investment isn't just in raw lifting power. It's an investment in a meticulously engineered, redundant safety framework designed to prevent the one-in-a-million catastrophe. With all these safeguards, from outriggers to anemometers, where does the operator's responsibility really start and stop? And when the tech is screaming warnings, how much risk is too much? This technical framework relies entirely on predictable loads. What happens when an unpredictable environmental force compromises the load moment? This is a question the industry had to answer with blood. On July 14, 1999, at the construction site of Miller Park in Milwaukee, Wisconsin, the massive Lamson LTL 2600 Transilift crane, known as Big Blue, collapsed while lifting a 408 metric ton section of the stadium's retractable roof. The accident was catastrophic. It killed 3 ironworkers: Jeffrey Wisher, William DeGrave, and Jerome Starr. The investigation determined the cause was a fatal failure to correctly account for the effects of wind on the massive, sail-like roof section being lifted. The failure was a multifaceted procedural one. First, the capacity of the crane was already operating near its structural limit, at about 97% of its rated load. Second, the wind factor was the variable that pushed it past that line. On the day of the lift, wind gusts reached up to 35 miles per hour at boom height. Expert testimony later concluded that sustained winds should not have exceeded 11 miles per hour for a load of this size and surface area. This massive discrepancy was a procedural failure, as the lift contractor and project team were cited for failing to factor the severe effects of wind on the load itself into the capacity calculations. The massive surface area of the roof section transformed the wind into a massive dynamic increase in load moment on the boom and the kingpin. The failure was not in the LMI reading the static weight, but in the failure of the team to account for wind in the lift plan. At the time, LMIs did not integrate real-time wind data. They only monitored load, radius, and configuration. The crane's main structural support, the kingpin, snapped under the stress, demonstrating that no amount of engineering can withstand the force of nature when its impact is deliberately ignored in the lift plan. The resolution of this industry tension was clear. The data collected by the anemometer must be integrated into the lift plan, not just seen as a passive warning. The ultimate responsibility lies not just with the machine, but with the engineers who sign off on the lift plan. The operator's job is to master this technology and exercise the engineering judgment that no computer can replicate. This human element, the callback to the initial problem, is what separates a safe lift from a structural failure. The operator isn't just moving steel, they're continuously confirming their adherence to an invisible, dynamic line. Thanks for watching Hard Hat Industries, your source for serious machines doing real work. If you liked this, hit like, subscribe, and turn on notifications so you don't miss what's next. Until then, keep your head down and your gear running.